My purpose for this presentation is to discuss the thinking that goes into examining performance through the technique of generalizability analysis. We'll start with the most basic design, where measurement object and measurement tool are totally independent. My emphasis is not so much on the mechanics of the analysis as on the logic behind it. In later presentations, we'll explore educational incest and other confounders. Finally, we'll discuss how to handle missing data and replications. This presentation isn't a simple-minded worksheet on how to measure, but rather an exploration of the logic behind it. Before we can look for answers, we have to know what questions to ask. In this case, there are two questions. Firstly, how big is the difference between objects? And secondly, how valid are the measured differences? The subjective analog perception of properties, such as dimensions, color, weight or sound, etc., suffices for the daily use, but for more serious purposes, such as legal, commercial or engineering, those subjective impressions have to be expressed in objective metrical terms. To measure a specific quality, we have to compare it to appropriately graded measurement standards. To paraphrase Engel's dictum, quality turns into quantity. Unfortunately, this process is often ambiguous, and repeated measures don't always agree. We have to find statistical compromises. As a hobby woodworker, I learned early: measure 3 times, cut once. But unfortunately, the converse happens not infrequently. Instead of measuring pieces of wood, let's examine how to measure human performance. Consider this fictional high school in the American Midwest. We are in the early 20th century, and people are starting to take education seriously. In the spring of 1921, the school board introduced an annual progress test for the whole school to evaluate how well the school fulfilled its purpose. After lengthy consultations, they decided to apply an identical 30-item multiple-choice questionnaire to all 43 students of grades 7 to 10 in the one-classroom school. In modern parlance, they considered it high school classes 1 to 4. These 30 questions had to cover 4 curricular years fairly and 5 topics, namely grammar, arithmetic, US history, orthography, and geography. A few weeks later, and the results are in. A table with 43 rows and 30 columns was used for tabulation, with a value 1 for a correct and a value 0 for an incorrect answer. The order of columns corresponded to the question item number. The order of rows was alphabetic by the student's name. The mathematics teacher added 3 index columns, a column G for gender, which was still unambiguous in 1921, C for class, in this case 7, 8, 9, 10, and ID for identity number, which corresponded to the alphabetic names. She also calculated the mean score, standard error, standard deviation, and variance for each student. I'm not going to bore you with the formulae. You can find them in any basic textbook of statistics and even on the Wikipedia. While index columns are important for sorting the data, you don't have to worry about the mean, standard errors, and deviations. The software will do all that automatically for you. But in 1921, there was no software. The teacher proceeded to plot the means and standard errors as box plot in alphabetic order, but found no rhyme nor reason. Any measurement results from the interaction between an object of measurement and a measurement tool. The object in this case, namely the subjects, is a group of 43 students, 22 girls and 21 boys in 4 grades. The measurement tool consists of 30 true-false questions in 5 topics. Together they form the so-called facets of the analysis. Generalizability analysis formally accepts the design as the product of object and measurement tool, where the customary order is from right to left. Next, we have to sort the data according to the design. Fortunately, the measurement tool, i.e. the rows, are inherently sorted because of the questionnaire form. Sorting the rows would have been quite a bit more work in 1921. Nowadays, the spreadsheet makes short shrift of sorting. We simply click on data and sort first by G, then by C, and within classes by performance mean. And abracadabra, the data are sorted. Now the graphics makes a lot more sense. I have simply color-coded the classes and added 2 gender symbols. On the left are the girls, on the right the boys. In both groups, performance is highly correlated with their class level. Please note that the total range of the boys is slightly wider than that of the girls. For 1 boy got everything wrong and 3 got everything right. But overall, there was no significant gender difference. To take things any further, we have to wait for another 40 years until generalizability analysis was developed. It is related to the analysis of variance based on the linear model, which we ultimately owe to Sir Francis Galton. I am trying now to explain the linear model for our case of the Lloyd Street School. The linear model calculates the score L of student S on item I as follows. Considering that student S is nested in class C, which in turn is nested in gender G, and item I is nested in topic T. L, the score, then is equal to the sum of a constant overall mean score value mu0 plus of 11 effects epsilon, 1 for each facet and their appropriate combinations. Each of those effects has to be thought of as an array of values, their dimensions equal to the sample size of the corresponding facet or combinations. The specific values then are picked from the corresponding arrays according to the specific facet value of G, C, S, T, and I. This pop-up actually anticipates the results of Brennan's Ur-Geneva calculations. The first column lists the designation for the effect, and the last column shows the estimated variance component value for this effect based on the total of collected scores. Specifically, for Lloyd Street School, the value μ0 comes out as 0.55. The variance for gender is essentially 0, and that for class is 0.09, etc. I must admit that this is by far the most complex part of the whole presentation. And you may want to spool it back to the start of this slide and repeat it maybe a few times until you feel that you really understand it. Then you understand generalizability theory. We no longer have to analyze the data by hand. We now can use ready-made computer programs such as GString to do the calculations in a few minutes. The target of the calculations are the summary mean scores corresponding to each facet of interest and their variances. But we have to properly format the data. Again, our trusty spreadsheet comes to the rescue. We simply delete the header row, which is in pink, which GString does not need, and the statistical results in green, which the Lloyd Street mathematician teacher had so laboriously calculated. But be sure to save the data in the correct file format, which is .csv, which stands short for comma-separated values. In a routine generalizability analysis, we designate the students as the facet of differentiation. In step 5 of GString, we have to indicate the sorting order of facets, where the asterisk indicates the facet defining a whole line. Step 6 describes the two crossed clusters, the measurement object consisting of the students nested in classes, which in turn are nested in gender, and the measurement items nested in topic areas. In step 7, we have to indicate that the two index columns can be ignored since the structure is defined by the order of the data. Finally, here are the results. We had specified the students as facet of differentiation. Gender and class are facets of stratification within which the students are nested. Topic and item constitute facets of generalization. GString calculates the ANOVA table, which we have already seen before, particularly the variance components for the facets and their interactions in the last column. E rho square is the generalization coefficient. Thus, inherent differences between students account for 72% of summary score variance. Ignoring the effects of gender and grade, from a statistical point of view, 43 students is a relatively small group, and the generalizability coefficient of 0.72 is really very good. But does that really answer our question regarding the efficacy of that particular educational institution? Yes, Students differ significantly by their intelligence and/or ability to learn, but it doesn't tell us anything whether learning actually takes place over the 4 years. To answer that question, we have to ask the question differently. This time, class level is the facet of differentiation. Students matter only insofar as they indicate where a new row starts in the dataset. The question items constitute the facet of generalization. Gender and topic don't matter. The ANOVA table looks quite different from the previous analysis. Now the generalization coefficient indicates that 94% of the summary score variance is accounted for by the class level variance, and this is exceptionally good. You can find the definitions of the terms PF, T, SS, MS, and VC in Brennan's Generalizability Bible. Thus, we have seen how generalizability analysis can answer some pretty fundamental questions. But we have to carefully think about the question we seek an answer for, and we have to pose the question correctly. Structuring and logically sorting the input data is best done with a spreadsheet. For the sake of transparency, I have to add that the displayed data were not authentic. They were synthetic thanks to G-string. Thank you for your attention.